All right, so we're going to review a little bit of what we did last Friday. We were talking about electric fields, and you can see here the slide that we ended on. I'm going to go to this here, and we talked about how does a charge A know that a charge B is even there to get pushed. So suppose A is not even there, right? B is charged. B creates an electric field. The universe around B, if B is charged, is different just because B is charged. And if we could put a little charge somewhere around here, it would get pushed either towards or away from B, depending on B's charge and upon our little charge's charge. We're going to call this little guy Q naught. That's like our analogy was if this is the Earth and this were like a little pin. And we don't know the Earth is even there. We let go of the pen and it starts getting pushed this way. We would know that there was something over. Well, for mass, for gravity always gets attracted. We would know something over here. But in this case, if this thing gets pushed, we would to the right. We would know that something was either to the left attracting it, or something is. If this gets pushed to the right, there's something over to the left repelling it, or something over here to the right attracting it. But we just know that there's some charges somewhere pushing it left and right. So this creates an electric field around it. And then we have a definition of the direction, or definition of the electric field as far as magnitude is E is, the electric field is the electric force from the field over the charge, and that is like this. The electric field is defined as, equal by definition, how strong the force is on some charge. And we were talking about if I doubled this charge, the force would double. But if the force doubles and the charge doubles, it shows the electric field from B in this case. In this case, the source charge is B, would be the same. So that's why it's a reasonable definition to come up with, because the electric field is dependent only on B. It's not dependent on that charge that you put there. Even if the charge weren't there, there's still an electric field from B all around it, even if there's nothing there testing or seeing how strong that field is. So we're going to go back here. It says the electric field is a vector quantity, and the direction of the field is the direction a positive charge at that location would be pushed. So if you were to say, look at something like, well, I guess I'll go back to here. If this were a positive charge, and you have something out here, and you pretend to put a little positive charge there, just pretend that's positive. A positive Q naught. It would get pushed that way, right? And if it was here, it would get pushed away. And if it were there, it would get pushed inward. But if it were negative, it would get pushed the opposite direction. So we have to come up with some definition. Like when I showed you the iron filings. They stood up no matter whether I put a north pole of the magnet close by or a south pole of the magnet close by. So we had to come up with some direction, either inward towards a plus or outward from a plus. And we picked, well, it's the direction that a positive charge would get pushed. So from a positive charge, all of the forces would be outward. So we could draw something like this, and draw the electric field looks like this. See all these pointing away? But that gets really hard to draw. Even the lines get on top of each other, like right here. They get on top of each other. So we can't really see where, if you're going from the middle outward, we can't really see what's going on. So let's look at this instead here. We've got a positive charge here, nothing around it. But if we knew this were positive, we could talk about the electric field, and we would take some point here, right? And it's going to get pushed away. That point over there is going to get pushed away. And so we could get this. That's where that came from. But like I was saying before, it gets hard to look at. So people said, we could draw that, but that takes forever to draw. What if we just draw something like a little bit easier to draw something like this? And let's actually get the lines all the way. I wish they had drawn them all the way down here. But from a positive charge, the lines go outward. And just like we had with gravity, where the lines are far away, the field is weak. Where the lines are close together, the field is strong. Okay, so that would be a positive charge. Here's the electric field from that positive charge. Now, what about a negative charge? If we have a so we could the lines don't really exist. We could draw a million lines, right? How many lines do we draw? We drew what? 1, 2, 3, 4, 5, 6, 7, 8. This one has a lot more lines. The lines don't really exist, but you can see where the lines are close together. The field is strong. The lines are far away. The field is weak. And if we had a negatively charged object, the lines would be inward because a positive charge gets pushed inward. So we're basically defining that the lines go away from a plus and the lines go toward a minus. Okay, something like that. Right? So the field lines don't really exist, but the field does, and man wanted to come up with a way to tell the difference between plus and minus. So we say they go towards a minus, away from a plus, and it helps us even make some predictions when we have like a plus and a minus all in the same, close together. So here's the deal. I'm going to go back to, we'll look at this. Suppose you have two plates, one positively charged and one negatively charged. And I'm actually going to go back over to this here and say, suppose we got a big, in fact, just suppose it goes on forever, bunch of positive charge. And it doesn't matter what I pick right now as far as this charge here, but just suppose it's a positive charge, a little positive test charge. This one here is going to push it this way, right? Straight down. This one over here is going to push it partially. It's going to push it that way. And this one here is going to push it partially that way, right? But when we add these together, this is pushing down and a little bit to the right, and this is pushing down and a little bit to the left. When we add these together, if you remember, one way to add vectors is to draw one. Suppose I draw this one, and I take this one. So this is, we'll call this 1, and we'll do 2, 3, 4, 5, 6, 7, like that. The forces from 2 and 3 are here. Here's the force from 2 down to the left, and the force from 3 down to the right. If I add this one and remove it, the force is still downward, straight down. Okay, so it turns out that the force from 1 will be straight down. The force from 2 and 3 will add up together to be straight down. And similarly, 4 and 5 will add up to being straight down, and 6 and 7 will be straight down, although they'll be more like this way from 7 and this way from 6. So it won't be as much down as, 6 and 7 won't be pushing this charge as much down as 2 and 3 are. But the point is that it gets pushed straight down. And as long as this thing is really big in real life compared to some little charge in here, it turns out that the electric field from this thing is pretty close to straight down. In real life, this thing is not going to be infinitely long, so it won't be perfectly straight, but it's very close to straight. And the same thing would be true if I had a negative charge, big piece of negative charge. All these guys would be attracting this positive charge down. And so the field lines from these would all be, since they're minus, towards them. And these would be going towards, because this is a minus. And all these up here would be going away, because this is a plus. What happens if I add these two together? This thing's still going to get pushed straight down. So you get a pretty uniform, pretty constant electric field between two plates, two parallel plates. In real life, you make them with pieces of metal, and they're big compared to a little proton, or not really proton, a little charged particle inside there. And so you get a pretty uniform electric field. So how does that? Why do we care? Well, we care because now we have a constant electric field, and it says the electric field between two parallel charged plates. And I'm going to cover this up. Between the plates, the field is relatively uniform. That is the same everywhere. So how does that help us? Well, because we had an equation here that dealt with the force. So suppose I know the field between those two plates, and it's a constant number, and I know the charge I'm going to put in there. I could find the force using this equation. The force is the charge. Oh, it's cut off your screen. Let me see if I can pause. There we go. The force is the charge times the electric field. So I could find the force on this little object in between these plates. And oftentimes, it doesn't even have to be plates that are parallel. They'll just straight up give it to you. They'll say, hey, the electric field in here, it's this number. So then that makes it much easier than Coulomb's law. People try to use Coulomb's law when this problem is actually much easier to find the force on some charged particle. In the middle here, you can just use the electric field times the charge to find the force, and I'll show you. I'm skipping these. I want to show you the pictures here. Here. So we've got this positively charged object, and it's going to get pushed which way? Well, these are plus and these are minus, but even if we didn't know this was plus and this was minus, the direction of the electric field is downward, so a positive charge gets pushed downward, right? Because the definition of the direction of electric field is the direction a positive charge gets pushed. So if the field lines are down, a positive charge gets pushed down, well, a negative charge gets pushed always the opposite direction. So if the field lines are down, a minus charge gets pushed up. So let's try something like this. What would happen if instead we have somebody tells you that the electric field lines are pointing left. I just picked one. The electric field is 2.0 times 10 to the minus 4 newtons per coulomb to the left. And you put in a charge there that is plus. And it's plus 1 microcoulomb. Okay? Which way is the force? Left or right? Well, the electric field is to the left. And if the electric field is to the left, a positive charge gets pushed to the left. And we could find that force. Just rearranging the definition of the electric fields. Fe equals Q naught times E. So it's just 1 micro 10 to the minus 6 coulombs times 2.0. I'll make that at least 2 sig figs. 2.0 times 10 to the minus 6 newtons per coulomb would give you a small little force of 2 times 10 to the minus 12. Sorry, 2.0 times 10 to the minus 12 newtons. Okay? What if it were a minus charge and it's 4 microcoulombs, but minus? Which way does it get pushed? Well, if a positive charge gets pushed to the left, the electric field lines were to the left. We know that a minus charge will get pushed to the opposite direction. So a minus charge is getting pushed to the right. So let's throw this was to the left. And then the electric force from the electric field on our new charge. So here's the deal. We're not worried about these. This guy's gone now. Forget about him. He's not there. There's some other charges. Where are they? I don't know. What charge are they? I don't know. How strong? Where? I don't know. But I know that there's an electric field. Somebody told me. They already gave me this number. 2.0 times 10 minus 4 newtons per coulomb. So I can use this equation. This one was on the plus. This one we're going to do on the minus. So the Q naught is the test charge. Not the thing making the electric field, but the thing getting pushed by it. That is 4 microcoulombs times this electric field. This is actually a pretty darn weak electric field. I should have made it bigger. 2.0 times 10 to the minus 4 newtons per coulomb. And that's going to give us 8.0 times 10 to the... Oh, what did I do? I'm an idiot. This over here. Shoot. Watch to the end of the video. 10. 10 to the minus 6, 10 to the minus 4. So 10 to the minus 10 newtons. Right. Okay? So if somebody gives you the electric field, finding the electric force is much easier than doing Fe equals K Q1 Q2 over R squared. And on top of it, you can't solve this equation using K Q1 Q2 over R squared because I've got this one charge. And I do not know where the other charges are making the electric field. The common mistake students make is that the one problem in A will give you this one, and then the problem B will give you this one, so like this. And students will say, oh, well, here's Q1 and here's Q2, but what's R? No, we're not finding the force between them. We're finding the force on them from some other charges. Like if this electric field is to the left, maybe there's a big charge bar of positive charge over here. Maybe there's a big bar of charge minus over there, or maybe both. We don't know. We don't care. As long as somebody tells us there's this electric field and it's pointed to the left, we can find out what we need to find the force on those charges in the field. And so this is actually a very similar problem to what I put in your notes. Back here, I just had the charges being a proton, an electron, and